Okay, there are two ways we can get derivative of f with respect to t. One way is just the composite. Okay. If x is x squared, if x is e to the t, then you write out the function t is e to the t squared, e to the t quantity squared, which is e to the 2t. And actually, what we have to stake on that. It's e to the 2t, it's not e to the t squared. You square e to the t, you get e to the 2t, not e to the 2 squared. So df dt would be derivative of 2t times e to the 2t, because of course derivative of e to the 2, well, we don't have to explain that. So that would be 2e to the 2t. Okay. Now the other form of the chain rule, of course, is df dx times dx dt. So what's df dx? And what's dx dt? E to the t, right? But of course, now since f equals e to the t, we do that real quickly, okay? It's two ways of looking at the chain rule. Now, let's think for a minute about what the chain rule means. It's the rate at which f changes when x changes. Not a totally rigorous statement. It's the rate of change of f with respect to x. Okay. But that's the feel of it. Okay. That's the intuitive idea, and it can be made rigorous. Then the x dt is the rate at which x changes and t changes. Well, it's the change of t that makes x change. So if t changes faster, x is going to change faster. And if x changes faster, f is going to change that much faster. Okay. So you multiply the rate at which t makes x change by the rate at which x makes f change. You multiply two rates. Well, what should you got? You multiply the two rates. So that's how you can understand the chain rule. And if you do it this way. No, there's one rate and there's the other. Okay. Still a product of two rates. That's the rate at which, two T changes, and that drives the change in E to the two T, okay? So, let me make sure I said that right, I think I did. All right, well, if you have a function of two variables, let's say x y equals 2x plus 3y plus 5. Plane. Now, instead of a slope of 1.3 or whatever it is here, your slope would be 2. It'd be pretty steep this way. And in the y direction, your slope would be that much steeper. Okay. But as x changes, your z value changes. As y changes, your z value changes. So x equals the square root of t and y equals 1 over t. Okay. Then first of all, df dx is n2 square root of, or dt is the derivative with respect to t of 2 square root of t plus 3 over t plus 5, which is going to be 1 over the square root of t minus 3 over t squared. If I did that right, check me on it. Okay. But there's another form of this. Alternatively, we have this. Okay. X changes at a certain rate with respect to t. Then we multiply that by the rate at which f changes with respect to x, because t drives x to change, and x in turn drives f to change. Just as case with one variable. So that accounts for how fast. Okay, x is in this direction. This accounts for how fast the function changes due to a change in x that's driven by a change in t. So t drives a change in x, makes x change a certain amount, and the graph goes up or down accordingly. Okay. And then same thing with y. Whatever this function is here drives a change in y, which in turn drives a change in the value of f. So work that out. Show me that that is gives you the same result. As I hope it does, because if it doesn't, I'm going to be really confused. Okay, so if you do this, it's probably 25% of your assignment, maybe even a little more. Okay. It's straightforward. This equals df dx is 2. And dx dt is 1/2 square root of t, right? And df dy is 3. And dy dt is -1/t squared. So you just write this down and write down each thing. And then do the arithmetic. And this comes out the same as this. Okay. So that's pretty straightforward. In the ones you have in your template, I don't see anything in your assignment that's any trickier than that. They're not trying to be tricky. Trying to do it. Now, what they say in WebAssign is do this using substitution, okay? And then do it using the chain rule. We're going to get the same answer both ways. Don't be tempted to just do it one way and put down that answer twice. Among other things, you do it both ways, which kind of checks if you don't get the same thing, you did something wrong. And if you just assume you got the right answer, and then WebAssign says you got the right answer, and you never did the other way, you miss an important part of the process, and it doesn't take long. I mean, you know, most of you wrote out a little more than this when you did it, because of the way you were assembling it, it was fine. But, you know, once you get used to it, df dx is just a simple derivative, df dy is a simple derivative. And actually, you know, I'm writing this wrong. I'm just being careless, but I've been working on becoming famous for that. Okay. These are partial derivatives. Need a partial derivative sign there. We'll get that notation right. It'd be misleading if you don't. In this case, we know what we're doing, but there's no point in doing it wrong. Well, it gets even better. Hey, let's say now, we'll just stick with the same f of x y function, because you know the derivative is a little more complicated. Well, you got to be able to deal with that easily. Okay. But the thing we got to do is now, what if x is u squared plus v squared, y equals uv? What do you think you're going to do with that? I want you to ponder it for a minute and see what you think you might do. If you have an idea, write it down. Good chance you'll be wrong. But there's a good chance you might be right too. So I just want you to think about it, and then I'll show you and explain why. Okay, now what we want to do with this is, first of all, yeah, we can substitute these things in here. Yeah, it's pretty clear that we get this function here. And now we can take the partial derivatives with respect to u, with respect to v. That's really easy to do. You know, we're going to get 2u out of this and 3v out of this. And this is going to give us 2v plus 3u. Looking like maybe I made a mistake, did I? I don't know. Let's see. Oh, it's 4u, 4v. Right now? Good, good. I can always tell by your expression. Lose your mind again? Yeah, the answer is usually yes. Okay. Okay. That's easy. But now how are we going to express partial f with respect to u in a form like this or this, I never did, yeah. I did. Okay. Okay, I've got this expression here, right? How am I gonna, what am I gonna do that would make sense in this form for the partial f with respect to u? Okay. So what's the partial of f with respect to u? Well, what is it about the change in u that makes that change? If u changes, well, that changes x. And that causes f to change. But also u causes y to change, and that adds to the change in x. Okay. So you would say f changes because x changes, and x changes because u changes. So this is the contribution of a change in u to the change in x, which drives a change in f. But u also causes y to change. So a change in u causes a change in y, which then causes a change in f. Okay, and you add those two changes. Then the other formula is okay, you're looking at how b makes f change. Well, b makes x change and x makes f change. But b also makes y change, which in turn causes f to change. Okay. So go ahead and calculate these expressions and see that they end up matching what you have there, and then look at how the operations are really kind of the same, but just conceive them a little differently. Okay. So again, they're pretty easy. Most of the derivatives in your homework are pretty easy. You have some that are functions that you haven't used a lot. I think there's an arctangent in there or something. Okay. So partial f with respect to x is 2. Partial of x with respect to u is 2 4u. No, 2u. Okay. If there's u squared. So partial of x with respect to u is 2u. And that is plus the partial of f with respect to y, which is 3. And then partial of y with respect to u, which is v. And it's in agreement with what it has to be in agreement with. This is just another way of getting the same result. This one is then 2 times 2v plus 3 times u. Very straightforward. 2v by taking the partial here with respect to v, and u by taking the partial here with respect to v. And that's 4v plus 3u, that matches up. Okay. Gonna circle that a few things about it. All right. I'm gonna rephrase this a little later. Okay. What's dy dx? Now, it's simple. I can easily solve this for y and take the derivative, right? I'm gonna get y equals negative x over 2. Dy dx is gonna be negative 1/2. If I did that right, did it in my head, who knows? But what we're gonna do is we're gonna take the derivative of this whole thing with respect to x. Okay. Now, when I did the derivative of 2xy, y is going to change with x, isn't it? Okay, so y is a function of x. Implicitly, I can explicitly solve this for x, but I could add a couple more terms, but I wouldn't be able to solve it explicitly. But I can still do what I'm doing here. And I get terms involving x, y, and dy dx. Well, the derivative of this equals 0. So this equals 0. So dy dx is what? It's negative x minus y over x. I just move these over on the other side to make them negative and then divide by 2x. 2 is all divide out. And I get this. Okay, well, that's just one example of such a quick differentiation. Okay. Going to do implicit differentiation with function 2 variables. I think how to make this clear. A couple of ways this can be written down. And I want to know. Okay. So, yeah, put find dy dx. And that's, of course, the derivative, well. Dy dx is going to be this partial divided by this partial, and if you regard this as a complex fraction, just remember the formula, you're not going to write. I'm not really going to try to make sense out of it like I did out of this. To make sense out of that, it's enough. You can think your way through making sense out of this. It's not that hard, but I'm not going to emphasize it. Okay. If you treat this as a complex fraction, you're going to divide this by this. So it's going to be partial z with respect to x times partial of y with respect to z. And the z's cancel out, and you get partial y with respect to x. Okay. And similar, instead of z, you can use f. It's the same thing. And neglected to put the negative sign down, they want to think about what it means. It's negative. So that whole thing about the fraction doesn't really explain it. But it's still a way to remember. You just got to remember to make it negative. So that's left. Let's just use this. Okay. So you got it works out. Okay, well, grooves are easy. Partial with respect to x is two y plus two x. Partial with respect to y is two x, and you got a negative sign in front of it. Is that clear? That's a simple example. If the twos divide out, and the minus is in front of the whole thing, not just the 2y, and you get a negative of same thing we got here. Okay. Okay. And that's pretty much it for that formula. It's at least a demonstration that it works. Okay. Now, if you have a function of three variables, you could do okay, you just got a function of three variables. You do the partial of z with respect to x. Partial f with respect to x. What it is partial of z with respect to x. Okay. The rate at which this function changes if x changes. Okay. So that would be no, we're doing partial z with respect to x. I keep my analogy straight. I'll do partial z. With respect to x. Which by analogy here. Could be this. Okay. And it's not right, I'm getting my notation mixed up. That's a partial of z. Yes. Partial f is back to x, partial x is back to y. Okay. Again, if you invert and multiply, you get a partial f. And then the partial f with respect to y would be I'm getting this mixed up. Shouldn't be getting it mixed up, but I am. Get my letters mixed up because I'm thinking straight. Let's do partial of f x with respect to z. It's a partial of f with respect to x divided by the partial of f. Or partial of f with respect to z, that partial of f with respect to x. Okay. Not like that, right? And I'm doing different derivatives than they are, and it's valid. But I want to give you the same formulas they give you in the book. So they would kind of reverse this partial of z with respect to x equals negative partial of f with respect to x or the partial of f with respect to z, and the partial of z with respect to y would be negative partial f with respect to y over partial f with respect to z. These are valid also. But if you're thinking of like f of x, y, z equals constant, defining a function of z. Okay, so if you got like this defines z implicitly as a function of x and y. You got some equation in x, y, and z, and maybe you can't solve that equation for z. Okay. Now, the example we did here, go back to this example. We could solve this equation for x. Okay. If we had an equation we can't solve for x, like put an e to the x in there somewhere. Okay. We wouldn't be able to solve that or put an e to the y in there. We couldn't then solve the equation for y in terms of x. But we can still do this. And we might as well do an example of that because we've got time. And we did, well, it's the same thing here. Okay, if you've got like the function z equals 3x plus 4y plus 7, for the function we were using. Okay, that could be written as 3x plus 4y plus 7 minus z equals 0. So your f of x, y, z would just be three x plus four y plus seven minus y, or plus z, whatever, minus z. Okay. Equals 0. And this would work, but it would be unnecessary because in that case, we can solve for z. If I'm getting any of this, probably best if I wasn't because I screwed it up. Okay. Now, my problem is we're going to pause for a second. I think I'm going to avoid this. I might not be. Yeah, okay. Okay, so we do this. Not have any interruption. Try to make the analogy clear, make it clear what's going on. So let's just say we got e to the y plus 2x squared y equals 0. We can't solve for y, but we can take the derivative with respect to x. So we want to find dy dx. We take derivative with respect to x of e to the y plus 2x squared y equals 0. And this gives us e to the y times dy dx, because y is implicitly a function of x. So we have to treat it as we would any function of x. And use the chain rule. Okay. And then this would be 4x y plus 2x squared dy dx equals 0. So we can rearrange that dy dx would equal negative 4xy divided by e to the y plus 2x squared. So this is f of x y equals e to the y plus 2x squared y equals 0. Okay. Now, make sure I follow the same form. We've got this all written on the other side of the board. Actually, I don't know what the heck it is. Okay. Using this. And we'll use this form. Let's just see that it turns out the same in this case. We already saw that it turned out the same here. Okay. So alternatively, we got this form with a negative sign in there for some mysterious reason. It comes out if we try to prove it. And we're going to see that it works in this case. Partial depth with respect to y is e to the y plus 2x squared. And what am I doing? Something's upside down. Yeah. Because I want this here, and it's obvious if you look at the complex fraction. Okay, so it's going to be minus the partial with respect to x, which is just 4xy divided by the partial f with respect to y, which is e to the y plus 2x squared. Okay, these are the same result. And if you wanted the partial f with respect to x with respect to y, if you wanted to regard x as a function of y, you just reverse these and you get the same. Okay. Now, if you have a function of 3 variables, I'm not going to do one that we can only do implicitly. We're going to say, okay, if we've got z equals x squared plus 2xy minus y cubed. And then clearly partial of z with respect to x is 2x plus 2y. And the partial z with respect to y is 2y minus 3y squared. Okay, I think I did that right. Now, if we let f of x, y, z equal x squared plus 2xy minus y cubed, then and then minus z. Okay. Then the partial z, partial of z with respect to x would be negative partial of f with respect to x over the partial of f with respect to z. If I wrote that down right, let's see. And it's kind of trivial in this case. Partial of f with respect to x is again 2x plus 2y. Need a negative sign out front. And the partial of f with respect to z is negative 1. So that is 2x plus 2y. It matches what it should match. Okay, well, you can do the same. Partial of z with respect to y, it's going to be negative partial f with respect to z divided by partial of f with respect to y. And it's y here and z here. And that's going to be, again, your 2y minus 3y squared. Negative of that over the partial f with respect to z, which is again negative 1. And that's going to match. Okay. Now let's say that we have, instead of this, let's say z is the square root of this. Let's look at x. Okay. And now we want the partial z with respect to x, the partial z with respect to y. Clearly, it's going to be a little more complicated because we've got that square root. It's just going to be like the x derivative of this over 2 times the square root of all this stuff. Okay. And that's going to be a little messier. It'll work out this way. Okay, so we do the function. No, it's not what I wanted to do. I knew what I wanted to do, and then I did the wrong thing. Okay. Here. Now we're not gonna get the derivative of f with respect to z was -1 each time, giving us kind of a trivial result. Okay, we're gonna let f x, y, z equal x squared plus 2xy minus y cubed minus the square root of z. So things get a little more complicated. We're gonna have a derivative with respect to z that's of f with respect to z. That's not going to be trivial. So partial of z with respect to x is going to be partial f with respect to x over partial of f with respect to z. Give myself a little more room. Okay, well, we're still going to get 2x plus 2y in the numerator. In the denominator, we're going to get we have to have a negative here and a negative here. We're going to get the negative of 1 over 2 square root of z, the partial of f with respect to z. Well, derivative of c with respect to z is 1 over 2 square root of z. And we'll have a negative sign. Just simplify it in my head here. Did that right. Okay. And I did because we're going to have a 2h plus 2 there. Of course, the square root of z. We solve this for z. And we can get it. So it's another application. It's still an application. We can easily solve this for z and just do the straightforward derivatives. I'm going to leave it at that. Okay, so it's another form of chain, and be worried about where that negative sign came from. I would explain that. I'll explain it next time. Okay. Okay, it works. Let you go early. Since I usually keep you about 4 or 5 minutes late, I'll let you go about 3 minutes early.